Hi there, this is Ajit. Welcome to Step by Step Data Science tutorial. So today we are in part 14, find principal component in PCA. So we will find principal component using PCA. So I will be using Andrew Ng Coursera dataset, and I will find principal component and do visualization of my principal component. So let's start. What is PCA? We will start first with PCA. So PCA is a principal component analysis, and it is used for dimension reduction. So if you have a data in 2D and if you want to convert my 2D two-dimensional data to 1D, what we will do is we will apply a principal component analysis, PCA. So let's say if my data is something represented here. So let's say so in this data set, so what we can say in this data set is suppose if my x and y, x1 and x2 component has this data set. So here my principal component would be is something like this. Let's say gonna be is something like this. So how we were able to find this principal component is we look at the distance. This distance should be minimum. So here this distance should be minimum. So we will find the minimum distance onto which to project my data so that we have minimum projection error. So this error should be this error or should be minimum. If this error is minimum, we also call this as projection error. Then this line is principal component line. What does this mean? This mean is this line denotes my all value that is in x2 and x1. All information is denoted through my green line. So this green line would be my principal component line. So how to compute the principal component analysis PCA is through these three steps. First, we need to convert our data to, we need to normalize our data and convert our mean to 0 so that my principal component always passes through the center point with mean equals 0. So also reason for doing normalization is so that my all features are in same scale. My all features are in similar scale. So if we use this, if we calculate a Z score, if we do a mean normalization, then my mean will be 0. So then my second step is to compute covariance matrix. So my formula for covariance matrix is sigma x minus x mu xi minus x mu divided by n minus 1. This is my formula. So my mean is, so we have standardized our value. So my mean is always 0. That's why we need to use this formula. Okay. And then third step is to compute SVD, singular value decomposition. So whatever we compute from covariance matrix, that would be my sigma. We need to pass that sigma here, and my CVD, singular value decomposition, will give me three output. So U, S, and this is V, U, S, and V. So what is my U? U is my eigen vector, and S is my stretch. So we will discuss about what is eigenvector, what is stretch, what is covariance matrix now. Okay, so let's start with covariance. Let's start with eigenvector. So what is eigenvector? Eigenvector is a vector. If a vector remains on its own span, even if we do several transformation, if my vector remains on its own span, then that vector is called a eigenvector. Okay, so suppose in this example, if my vector is 3 0 1 2, so if my vector this is 3 0 and this is 1 2, so this line is 1 2. So here my eigenvector will be 3 0, because even if we stretch or do a transformation by 3, my value remains the same. My transformation does not changes. So here my stretch factor is 3, and this 3 is called eigenvector. Eigenvalue, sorry, eigenvalue. So to learn more about eigenvector, so eigenvector gives us the principal component in PCA. So if you want to learn more about eigenvalue, you can refer 3 blue 1 brown series. They have amazing visualization done to explain eigenvector. And the second one is covariance matrix. So covariance matrix gives relationship between independent and dependent variable. So this is my dependent variable and this is my independent variable. If my plot is something like this means my data is increasing positively. If I have plot something like this, my data is decreasing negatively. If I have plot something like this, there is no relationship. There's no relationship. So if this means with every unit increase in independent variable, we see increase in dependent variable. Every unit increase in independent variable, we see increase in dependent variable, and so on. And here with every unit increase in independent variable, we see decrease in dependent variable. So this line shows negative covariance. So it has some value. If my covariance is positive, that means it is flowing in positive direction. If my covariance is negative, that means it is going in negative direction. If it is 0, if my covariance is 0, that means we don't have any relationship. So we discussed about eigenvector. Eigenvector gives us the optimal vector. We can say like a vector, or that even if we do any transformation, or we even stretch or do transformation, the span of that vector line eigenvector does not changes. It remains same. That's why it's a principal component vector, because that point, that line, that vector will always be same, even we rotate or stretch with some value. So here this line is what we call this line. This line should pass through center. So this figure should be something like this. So this should pass through center. So if my x value is here, it's something like this, then the optimal PCA should pass through my center point. So it will be something like this. So here my data can be something like here, you can say. So it passes through center. So these are my 3 steps to compute principal component. And so a brief about what is SVD. So SVD is my singular value decomposition. So what does that mean is, let's say I have my x vector 1 by 3 and my a vector is 2 1 minus 1 by my 2 1 minus 1 and 1. If we need to multiply a times x, so if we need to multiply by 2 1 minus 1 1 times 1 and 3, then what would be, this would be like 2 plus 3 minus 1 plus 3. So this would be something like 5 and 2, right? 2 plus 3 5 minus 1 plus 3 2. So if we plot if we initially plot 1 3, then it would be somewhere like this, 1 1 2 3 here. This would be my x, right? 1 3. So yeah, so my 1 3 would be something like this, right? So if we do a multiplication, my matrix changes to 5 2 1 2 3 4 5 1 2. Something like this. So initially my 1 3 now has been, if we do a rotation here, this has been rotated by theta. Suppose it has been rotated by theta and it has been stressed, right? So 1 3, this 1 3 component 1 3 5 2. So this line has been rotated and this line has been stressed, right? So whenever we do a matrix multiplication, what happens is first rotation and then stretching, right? So rotation occurs through this component. So rotation by theta means we are rotating through this matrix, and stretching means like we are doing the stretch through this matrix x alpha 0 times alpha. If my alpha value is equals to 1, that means we are stretching, and if my alpha is less than 1, that means we are compressing. Okay, so what happens if we do a matrix multiplication? It simply rotates and stretch, rotation stretch, right? So if my alpha is equal to 2, then my a will be 2 0 0 2, and my y will be a times x. So now my y, what will be my 2 0 0 2. So my x is 1 by 3, right? 1 by 3. So what would be my new y? 2. This will be 0. This will be 0 6 2 6, which will be somewhere like 1 2 1 2 3 4 5 6, somewhere like point would be somewhere like here. So here we can see this line has been stretched out by 2.2, right? So this tells us, the alpha label tells us the stretching, how much stretch we have done, right? So here likewise, so here once we do a SVD, what we get is, first we get u, that is a eigenvector, and second one is the stretching, how much stretch we have applied, right? So if we do a multiplication of y equals u times s, so here we did y equals a times of x. This gives me the vector, right? Vector. So here if we do a multiplication of y times s, that will give me the vector, that will give me the line of principal component line, that will give me principal component line. Okay. So this is how we will plot our principal component. So let's start with these three steps. First, normalizing, mean normalization, then we will compute variance, covariance, and then we will compute eigenvector through SVD, single value decomposition. Yeah. So this is my data set. So if you look at X, it has two values. So let's plot this first. We have to plot. So take X0, comma, let's check how my data looks like. So here we can see my data looks like this. Now what we will do is, my first step is to do mean normalization. Okay, so I will create a class. I will create a class for my PCA. So let's say my class is PCA. So first will be my feature normalization. Feature normalization comma X. So this will be my mu will be np dot mean times X. This will be 1 because we are taking row wise. Some std will be np dot std X. X is equal 0, and my z will be X minus mu divided by std. Now I will return here z mu and std. So this is my feature normalization. Let's check if this is working or not. So let's create an object PCA. Now compute my X norm, my mu, standard deviation, std equals PCA dot pass my X variable. Okay, this is working. Now what I need to do is I need to find my covariance matrix. Covariance, and so my second step is to compute covariance matrix and then eigenvector. So PCA we pass self comma X. So my formula is X times X transpose divided by M. So M comma N will be my shape, X dot shape. My covariance matrix sigma will be equals to 1 by M X times X dot transpose. So we need to do matrix multiplication here. So to do matrix multiplication, we do add the it. So now we get sigma, then we will calculate U, S, and V. So it will be SPD. So I have already imported my SPD. And then pass my sigma. This will return. Then I will return U comma S comma B comma sigma. Okay. I'll check if this is working or not. So I will return U comma S comma B comma sigma equals PCA bracket X. Let's keep this name as principal. Okay, let's find. This is fine for now. We will change later. So if we run this, let's restart it. So now what we got? Let's check my U. U is my eigenvector. Okay, and S is my stretch. So stretch should be in 2 by 2 dimension. Let me check. So we need to pass X norm. Sorry here. Okay, now let's rerun. Okay, so this is my stretch, and U is my eigenvector, and sigma is my covariance. Okay, so here if we look at my covariance, so my covariance is 0.73. What 0.73 means? Means looking at this plot. So looking at this plot, so 0.7 is, we can say my covariance is positive. So my direction of principal component line will be positive, right? So the sigma is my covariance. Yeah. Now what we need to do is, now we need to visualize my PCA. So that what I said. So to create a vector. So here what we did a multiplication of A times in X. That gives us the line, this vector, 5 times 2. So here my stretch is denoted by S, and U is my eigenvector. So to get this line, what we need to do is we need to multiply our U times S. Okay, so why we need to multiply? So that we can visualize our output. Now what we are doing is we are visualizing our output. Okay, so here my first component is this, and then and again then plt dot plot bracket this is not okay. So what we need to do? So here my mu is, if you look at my mu, so my mu is 3.98 for one coordinate and 5.00 for another coordinate. So what I need to do is I need to plot taking this mu. So this is my visualization, right? So what I will be doing is, so this is my visualization for that data. So my mu is mu here is 3.98. Yeah. So what I will do is my x coordinate will be mu times mu plus u times s, u times s. Okay, So why we are doing mu plus? Because my mean starts from here, so my principal component always starts from mu. That's why we are adding mu. Okay. So will be first coordinate will be mu times 0. We will take, and then we will add s of 0 times u of 0, u of 0. This will be my transverse, and then we will take 0 because this value has two output, right? And then once we take this, then we will close this bracket, and then again we will take mu of 1 comma mu of 0 comma mu of 0 plus. So this will be my one coordinate, and then this will be my another coordinate. Likewise, mu of 1 comma, let's see this in bracket, mu of 1 comma mu of 1 plus mu of 1 comma, this will be my mu, sorry, mu plus s of 0 times u of 0. And this will be transverse 1. Okay, let's close. Let's color this with black. Okay, black, and give line as 3. Check this again. So this is my one. This is my principal component. One principal component line, and another line is for s equals 1. For u, even for 1, s1, u 1. Just to close. Let's do once again. Copy this. This was working, huh? So this time my u will be 1, s will be 1, s will be 1, 1. Okay, so this is my principal component line. So here if we view, this is u, this is u, this is my, this u is my eigen vector. This is my principal component vector. So this is how, this is my principal component. that we got. Okay, so eigenvector. So this is my principal component, and what we did is we plotted our principal component by multiplying stretch time rotation. Stretch time rotation. We followed this convention. Stretch times rotation. Why we did stretch time rotation? Because to get a vector line, to get a principal vector line. So here, if we do multiplication of a times x, we got 5 times 2. So this is the vector line. Likewise, to get a optimal vector line, we need to multiply it with eigenvector and stretch. Okay? So if we do a multiplication, this will give us the plot. So this is my principal component line for this data set. Hope this video was informative and it gives you some lesson. You might have learned something. If you like my channel, please subscribe and like. Thank you so much.